Hey there. We use these things every single day, but for most of us, computers are basically magic boxes. They just work. Well, in this explainer, we're going to crack open that magic box. We're going to see that it's not magic at all. It's just a really logical and actually understandable system. All right, let's get into it. I mean, really, have you ever stopped and thought about it? What is actually happening in those billions of little operations every single second when you do something as simple as click a mouse? It feels like sorcery, but I promise you, by the end of this, you'll see it's all based on a pretty simple and elegant process. So here's our game plan for pulling back the curtain. We'll start with the big picture, this three-part system. Then we'll look at the physical machine itself, the instructions that tell it what to do, how those two things actually talk to each other, and finally, all the different ways these systems can be set up. First up, a three-part system. The most important thing to get right off the bat is that a computer isn't one single thing. It's a team, It's a collaboration between a few key players that all have to work together to get the job done. So what is a computer, officially? Well, the textbook will tell you it's an electronic device that stores, manipulates, and retrieves the data. But honestly, the most important word there is system. That's the real key to understanding it. Don't think of it as a single object. Think of it as a team, a group of different parts all working towards the same goal. And who's on this team? Well, there are three main players. First, there's you, the user. You're the one giving the instructions. Then there's the hardware. That's the physical machine, all the parts you can actually touch and see. And finally, you've got the software, which is the set of programs that acts as the director, telling the hardware exactly what to do.
To make this super clear, let's use an analogy that we'll keep coming back to. Think of it like a kitchen. You, the user, you're the chef. The hardware is the physical kitchen and all the tools, the oven, the fridge, the mixing bowls. The software, that's your recipe book. And the data you're working with, those are the ingredients. See? Simple.
All right, so we've met the team. Now let's step into their workspace. We're going inside the kitchen to take a look at the hardware. This is where all the actual physical work of computing gets done. So all that hardware, it operates on a really basic three-step cycle. First is input. That's you providing the data, kind of like the ingredients arriving at the kitchen door. Second is processing. This is the computer's brain doing all the work, just like the chef cooking the meal. And finally, there's output. You get the results. The finished dish is served. Now, let's peek inside that brain, the CPU. It's not just one thing. It's actually its own little team of specialists. You've got the arithmetic logic unit, or ALU. That's the math genius. It handles all the calculations and logic. Then there's the control unit, the CU. It's the manager, directing traffic and telling everyone else what to do. And finally, the memory unit, or MU, is kind of like a notepad, holding on to whatever data is being worked on right now. It's this whole setup that makes it so ridiculously fast. Speaking of memory, there are two main kinds you need to know about. There's primary memory, which is short-term, working memory, like RAM. Think of it like your kitchen countertop. It's where you put the ingredients you're actively using. Then you've got secondary memory, which is your long-term storage, like a hard drive. That's the pantry, where you keep everything you're going to need for later. Okay, so we've got our kitchen and our chef. But how does the kitchen actually know what to make? Well, that brings us to our third section, the software. This is our recipe book. This little diagram here shows the whole relationship perfectly. At the very center, you've got the physical hardware. Wrapped around that is the software, which is the essential bridge connecting you, the user, to the machine itself. And it's all organized in layers, with each layer doing a different job. We can split software into two main types. First is system software, like your operating system. It's the stuff that manages all the computer's resources. In our kitchen analogy, these are the general rules of the kitchen. Safety procedures, how to keep things organized. Then you have application software. This is for specific tasks, like a word processor or a game. That's like a specific recipe for making, say, a chocolate. So, we have our recipe, but what happens if our kitchen tools only understand a totally different language? Well, that brings us to a super important step. We gotta translate that recipe so the machine can actually understand what we want it to do. And this right here is maybe the most fundamental truth in all of computing. Underneath all the slight graphics, all the user-friendly interfaces, a computer only understands one thing: machine language. And that language is made up of nothing but streams of ones and zeros. That's it. Every single thing your computer does, from showing a movie to sending an email, boils down to a sequence of on and off signal. Now, as you can probably guess, writing code using just ones and zeros is, well, it's a nightmare for humans. So, over the decades, we came up with easier ways to do it. Back in the 50s, we got symbolic languages that used simple memory aids. And by the 60s, we had what are called high-level languages, like C or Java, which are way closer to how humans actually think and speak.
So, how does our human-friendly recipe get turned into the ones and zeros the hardware needs? It's this really cool four-step translation process. A programmer writes the code. Then, a special program called a compiler acts like a translator, turning it into machine-readable code. After that, a linker gathers all the different pieces of code needed into one single package. And finally, a loader takes that package, puts it into the computer's memory, and presses go.
Okay, let's get to our final section and see how this all comes together in the real world. Just like kitchens can be small home setups or huge industrial operations, computer systems can be arranged in a bunch of different ways. We call these computing environments. The one you're most familiar with, probably the one you're using right now, is personal computing. This is a totally self-contained system, your laptop, your desktop, where all the hardware is right there, dedicated to serving the needs of just one person. It's your personal kitchen, right at home. Then you've got the client/server model. This is basically how the internet works. Your computer, the client, makes a request like, hey, I want to watch this video. Then another, way more powerful computer, the server, does all the heavy lifting of storing that video and sending it back to you. And when you're talking about massive operations like Google or Facebook, you have what's called a distributed computing environment. In this setup, the work is shared seamlessly across tons of different clients and servers, all working together over a network. It's like a global chain of thousands of interconnected kitchens all working on this same giant meal. So what's the big takeaway from all this? It's that the computer isn't some magic box. It's a logical, understandable system. It's really just a collaboration between you, the user, the chef, the physical tools you can touch, the hardware, the kitchen, and the recipe that provides all the instructions, the software. And really, that puts all the power right back in your hands. If the computer is just a tool that's following a recipe, the only real question left is, what are you going to ask it to make next?